So I this talk, and I must say, like some speakers, I'm not really in the mood for celebration because Jean-Pierre was a very close colleague. We were office neighbors. We have neighbored offices for many years, and so, for example, I saw he was always welcoming visitors, PhD students, and postdocs who came to his office asking for advice. And sometimes Jean-Pierre was not there, so they asked me as a guy next door. And, this didn't always work, okay, but most of the time didn't work, but still I had some very nice contacts this way. And I got a kind of revenge by asking Jean-Pierre for advice for all kinds of tricky matters, because as you know, Jean-Pierre was had a very broad view of things. He was French word is au-dessus de la mêlée, and that was extremely helpful for all these tricky matters. For mathematics, I must say part, because you also know Jean-Pierre using them very successfully for algebraic geometry. And he made these tools and work popular by giving talks and courses that I followed. And each time I was impressed by the clarity of his talks and insight. And I could also understand this. After 1 week, so I had to work with my hands on very basic things, and that's why the talk is something in positive characteristics. Then you don't have many tools at your disposal. Just algebra. I'll start with will be algebra of characteristic P, could be positive, and in this talk a smooth projective variety over K. Some kind of basic objects, and I'll begin by discussing cyclic coverings. Which are a very classical, useful construction. And a second its divisor by S by E. This is some effective divisor on Y. And then the construction gives you some well, a pullback of this divisor gets divisible by n. So where D is a divisor and if E. So this is okay. So that's one way to present this construction. The use of this is the following. You start which is Q divisor on Y. And after pullback, you get a honest divisor with integral coefficients. And this has been used in many ways. For example, to prove vanishing theorems when you need this trick at some time. And also to construct interesting varieties. Because you start with very concrete objects, Y and this. And you use some nice varieties. For example, some surfaces of general type were constructed in this. Gives some details on this, which, by the way, is very. I'll follow a very pedestrian approach, which is much less elegant, but what I want to do. So. Construct, in fact, is a direct image of the structure sheaf. So this is enough to. And you take this. The sum of L to L. Define a multiplication on this. I this is the correct range, so A plus B is smaller than N. And, you get something which is too small, so you have to put it back here. You put it back in this way. And you have to multiply by the section, which goes from OY to L to the N. So this puts you back in place. Kind of pedestrian description, because in this way you see some group action on this, which corresponds to the grading. This is a grading by Z model, and mu N, which is a on X. Well, if you some T in mu N and some F in L the minus A, multiplied by this. Because mu and are just these ones, those ones. Wait. What you see with maybe a bit more care is if you restrict I to support of D, Y minus support of E, this is a and D is a it's completely wrapped along this divisor D. Okay, so Now let's the geometry of X. I'll begin with a case which what happens in characteristic 0. Suppose that n is prime to the characteristic. Then what is that X is normal. The singular by one in some varieties or and usually not smooth. For example, if you have a smooth divisor because of this, you get singularities. But you can resolve singularities in characteristic 0. No. No. No, X is irreducible. You just see this here. If you go to the fraction field, then you extract the nth root of the section. That's always true. Not even that. I think so. Ah. And you're correct. Okay, so things go well, and the thing P divides n, then all the think of this mu n as a group scheme, and group scheme is just consider all points with values in bars over ground field, so mu n of some algebra R. That takes the roots of unity in R. And even if you don't have roots of unity in your original field, you get. For example, if you take mu p of a field, this should be a field extension of small k, then you just get 1 because, as you know, P minus 1 is and if you look at mu p of the ring of dual numbers, you get something really large, which is 1 plus k epsilon. Because if you raise this to the 5th power, this coefficient disappears. Okay, so by working formally with group schemes, you get then is really different because X may be singular in codimension 1. Again, under the assumption that reduced. And another pathology is there are So I'll give happen. And the first impression you have when you work in positive characteristics is that nothing works as usual. And if you're lucky or work hard enough, you can find some kind of substitutes, and the talk illustrates these principles. Let me, as mentioned, start with the smallest example. I spent lots of time on this example. You just take y to be p1. So it looks safe enough. And then concrete. Now what? Sorry. I sorry. Put formula in two variables, which is degree p, and to get a reduced divisor as required, polynomial is square free. And this polynomial is a product of p linear. I assume they are pairwise distinct. So now you can describe this x, the projective this equation. Okay, that's how it is. And what you see is the projection to y, which is p1. It's just a linear projection, which is given by this coordinate y. And I should identify the action of up on this p2. In homogeneous coordinates, it can be given by this. And you remember t to the p equals 1, so the equation is invariant. So all of this makes sense. And now I will try to understand which kind of curves you get here. This is very easy to see that is singular. Not consider this case, and it's smooth along D, which is the zeros of F and Z. But what is that characteristic P phenomenon, even if it's given by an equation of high degree. So the way I see it is you consider this map I here. And it's purely inseparable morphism, so of degree P. So at the level of function fields, you get this extension. And again, this is only of the VP. If you play with the Frobenius, you see that this is exactly the field of Pf power. The Pf power from yes. This is smooth along D. Singular at some points outside D. The singular points provide the equation take y equals 1. These are the zeros of the derivative of f prime of x equals 0. So they are outside of the zeros of the polynomial because it's square. So this is, sorry, I didn't give detail, but this really a simple calculation, a bit more tricky. But you see that ours is transcendental, so the original field is transcendental. Okay. So what you get is indeed a single curve, and it has a unique resolution of singularities. It's a big word for the that's the only way to resolve singularities. And the claim is here you have an action of mu p on this object, and it's left to an action of mu p here. So if and the exercise is that such an action is tricks. You get exactly p fixed points, which are the zeros of this polynomial, the roots. This. So this example, in line, not too good from the view of the geometry. However, you can upgrade this singular curve to a smooth projective surface, and that's what we will do next. So let me be specific on this. So you start, which is of course a group scheme, and so on. But you can always put it in a smooth, smooth algebraic group. And one way to do this is in an elliptic curve. To do this is as follows. Take the kernel of the multiplication by n, which goes to C through C. If you think over the complex numbers, you get z mod n to the square for all n. And in characteristic P, things get a bit different because of n could be divisible by p, but this is still generally z mod n times mu n. And this works for all n if the curve is general. The technical word is ordinary. But, if you take any, you get, first of all, you have less p torsion points than usually. You only get z mod p, but there is still one mu p. So you can. What you do is the quotient of p acts simultaneously on both sides. So let me write explicitly the action. Is always the same. T is something in u, and then cx. So I can act on this C by translation, and on this X by the given action. Okay. Okay, and then you see this positive surface. Because it's a product of two curves by some finite group. And it comes these two natural maps. The first one is you can forget part of this quotient. You can send this to, well, yes. Is it what? X mod mu p. So you just forget the first copy and you send it to this, which is P1. And well, see this elliptic curve C acts on the surface S by translation on itself. This commutes with the group action, so it descends to an action. And this map that I just wrote is the quotient by this action. And since this quotient pi the principal wave divisor E, you get a principal over there away from and then you gain something by this small trick, because since you have a principal bundle over a smooth variety with a smooth fiber, then the total space is smooth. So you see this surface is smooth above this. And you get another map, which is the other projection as to C mod mu p. I don't know which name. This fibration with fiber X, which is maybe a bit new or well unexpected. Statistic 0 would not have such maps because of generic smoothness. Well, sorry, I didn't. I should say that is smooth. The main part of this construction, and I didn't fully explain why, because you see S is smooth away from the divisor E here, and along this divisor, what you do is take the quotient smooth variety, because X is smooth along D. And you take the quotient of this smooth variety by something, and this is still smooth. Because this is this theorem of Serre, that if you start with a smooth variety and put faithfully flat morphism, then the image is still smooth. Okay. So, with some hand waving, proves this smoothness assumption. Okay, so you get finish this discussion. What you get is an elliptic surface fibration between being this F. So general fibers are copies of the elliptic curve C. Which is, it contains, is covered by rational curves, which are the fibers of this map. the curve C, and it translates. But it's all singular. This S is a minimal surface, because if you had such a rational curve on S, then you map it to this quotient, which is a honest elliptic curve, so it's contained in some fiber, and then it must be some copy of X. So that's a kind of surprising example from the point of geometry. But you see, it's constructed in a very way. The rest of the talk, I will discuss some generalizations of which object you get this way. No. This has even no rational section. Well, is it? Well, if you had a section, maybe some curve gamma, you take the map C times gamma to your surface, where C acts by translation, and you find that it's an isomorphism. So the vibration would be completely trivial. So this surface are kind of exotic construction. Just take the smallest example of topological construction and push it a little bit further. So now I will, well, yes? Ask Mathilde. She has a paper on this. Okay. I don't remember. That's why. Well, I'll give some reference. For this surface, dimension is minus infinity, but you also find by of this construction that I'll explain next. Okay, so let me try some generalizations of this construction. So you may safely work with mu p if you're not too familiar with this object. And we'll consider a curve with a g action. And all the action need not lift to the normalization, so I will say that X is G normal if normalization, but adding a G everywhere. G curve with and G which is finite, of course, by rational. F So if you don't have any G, you find some geometric version of the condition for a curve to be normal or smooth. And here, as seen in this example, you get a slightly new. And now it's easy to see that this this is really some exercise that I will not do, but I can give it to students course on algebraic geometry. There is a converse to this. If you have a principle with x mod g smooth, then the total this is also very easy to see. And this is not a full description of G because, as you see, you may have fixed points which prevent your quotient to be a principal bundle. And so you have to do something with fixed points. And this part I will not do in detail by lack of time. Another observation is every the G normalization. This is the normalization, some easy trick. So until now, these are sizes on this notion. But then comes a kind of basic that for the usual normalization, a very convenient description in of commutative algebra, via integral closure. And I don't know any version of this in this setting, or I know some of them. It's extremely messy. So rather than trying to work with this notion, there is a trick to reduce this G normality notion to smooth ones. And this is what I will explain next. So for this, you have to the trick of algebraic group, which I will write. Well, that's the notation. This is always possible because G in some GLN, and this you know honest finite group. You just take the regular representation, and this. Which is a interesting case. So it's G in some abelian variety. This is a of so you can use both or combination. And once you have this, you can put your curve in construction as a, but with this big group. Well, now you define the action in a similar way. Well, Okay. So I just copy the. Well, with the group is maybe not commutative, so I have to be a bit more careful. Now we still have this, well, let me write this x sharp to be this make of that. And this has and map it to and now the result, maybe I state it as a theorem, is that x is G normal if and only if gadget is smooth. Well, here I would have this should be a G curve. And you have this equivalence. Let me comment on this. Actually, I stated as a theorem because it's useful, but it's also very easy to prove, because the right condition should be G-check normal, if you do this formally. But since G-check is smooth, this is the same as being normal, and looking at singularities, you see that they are not. So it's really not a big deal, but you see it's very practical. So how to understand it? Well, there's a fancy version which says that the quotient stack is smooth. And the fact is, in this situation, this quotient stack is the quotient by G-check. So this is equivalent to the smoothness of this. I must say I don't really understand what this stacky word means. I can use, I can just do a first exercise in stacks to prove this. That's my understanding. But still, I think it's good to mention. So this you see some useful corollary, which is that if x is G normal, it's a local complete intersection. So it's a singular curve, but it's not too bad from the viewpoint of singularities of curves. The reason is, again, very simple, because you have this x sharp, which is now a smooth variety, and you have a morphism to a smooth variety here, homogeneous space, and it's very easy to see that this morphism is faithfully flat, so the fibers are defined by the correct number of equations. That's the proof. So once you get it, think, but if really, if you get a principal bundle, if you get, for example, fixed points, then this imposes additional conditions. For example, fixed points should be smooth. This is, and if you have points with isotropic groups, then it's a bit messy. So, but this is what I had in mind. Other questions? Yeah. Again, it's I'm ashamed to answer because it's really some. So yes. So you have this quotient. Okay. Suppose y is not smooth. Take it's a normal model. Okay, the curve, and then take the fiber product. You take some kind of main component, which is the one which dominates this. And then this map is birational, finite, since this morphism is invariant, and this one is this is a G curve. So it's an isomorphism, and by taking the quotient, you get an isomorphism here. So I solved the exercise. Sorry, that's I mean, this is the level of this tricks that I mentioned here. That's nothing big. So. Okay, so on the left, I want to mention two things. First of all, if your group G is contained in an elliptic curve, and X is G normal, what you get in this way, taking this C as this check, is a surface as we already discussed. And you may wonder what kind of surfaces you get in this way, and the answer is surfaces, smooth, with a non-trivial action of an elliptic curve. Which here is a translation action on of the curve on itself. And that's something which is quite obvious to show, but it's a fact. And you get geometrically, it means some kind of isotrivial elliptic fibrations which in this case are again this S to Y. Isotrivial is a bit stronger than the usual sense, saying that all the general fibers are the same, because you need this action of an elliptic curve, which is a stronger requirement. Okay, and this have been studied recently. McCann on the archive 1 month ago, and in this paper they needed some for the canonical this G normal curves. So I will state such a formula. Well, not in the most general case, because I don't know how to prove it, but it's in some cases which covers many examples. So you take a G normal curve, assume G is which means concretely it's a product product of cyclic groups. Well, these are analogs of the finite abelian groups of classical algebraic geometry. And then the statement is as follows. Let me state it first in a loose way and then try to define the objects. So this would be the relative canonical bundle, and this should be over the points of y of something like 1 minus 1 over ny I have to define ny is the order of the isotropic group at x above y. Okay, so that's this formula. To recognize some classic formula for what's the name? Orbital bundles. And for cyclic covers, well-known formula if the order is, if the degree is prime to the characteristic. But here there is a small problem of definition, because this relative canonical bundle has to be defined properly. We work in a singular variety X, so which is not normal. The usual way to find this canonical bundle does. It's not too wise to use differential forms in this setting, because this morphism from X to Y is sometimes purely inseparable, so it's a bit risky. And the only way I can work with this is to use, so let me quotation marks and define correctly the object. So well, consider the relative dualizing sheaf omega x mod y. Abstract algebraic geometry, you have a finite flat morphism from dualism sheaf. Okay, this we can work with, and it is possible. You have a local complete section. It's a good object. It acquires a kind of concrete meaning if you write it. Well, the algebraic definition is something like this. Okay, which makes sense. And this is a sheaf of OY modules, but it has a structure of a sheaf of OX modules via the action of OX on this side by multiplication. And, so you have to manage with this object, but there is a canonical global section of this. Which I will write as x mod y, because if you look at all these homomorphisms, there is a nicer one, which is a projection to the invariance. So you see you have a diagonalizable group action, so you have a grading of this object, and you project to the degree 0 part. Okay? And then you get this section, and the claim, well, the correct statement is that the divisor of this section is the right-hand side. And okay, here you have a Q divisor, some fractional coefficients, but it's a kind of cheat because these the coefficients are killed by this. And you can rewrite this in the following way. I think this is something like n of x, g x. It's always confusing. This is a G orbit, and you find some honest formula with integral coefficients. So that's now maybe the next. Time I'll get proof. So how much time do I have? 5? Okay. Well, I'll cheat more and more and sketch a proof of this result. Proof is not very clever because you reduce to a local computation. The idea is very forward because again, when you work with this relative dualism sheaf, which is defined in a completely algebraic way, it behaves very well with respect to all kinds of reasonable maps. For example, open immersions, flat pullbacks. And you have an explicit section and its divisor, so you can move things, try to reduce to some rather nice description of the actions of this diagonalizable group schemes. Maybe sketch as follows. A point, then you have its isotope group. And well, take this in a schematic sense, okay, everything. And what you find is that the first this is a familiar fact for smooth curves and actions of finite groups, and this still holds in this setting. It requires some work. And the second step is to describe the at this point. What you can do is take quotient by this subgroup, and then but what you should do is your map. And now in characteristic 0, The second map is étale at the image of the lines of here and here are isomorphic. And this is a kind of a basic result in actually in Galois theory, if I remember correctly. I learned it in the book of Serre on local fields, because it's a basic source for what happens if you look at ramification of curves in an algebraic way. So again, in characteristic 0, this doesn't affect the canonical bundle. But in characteristic P, you have some trouble because, for example, if your group has order a power of P, all maps are purely inseparable, so there is no way to get an étale map. But the thing is, bundle over the Riemannian group. Remember, this group is commutative, so I can do this in a neighborhood of this point Z. So this is well understood, and this map and so you get two explicit maps. The good thing with principal bundle business is that the relative canonical bundle is trivial. And this is another exercise in finite group scheme. So this again doesn't count, and for this just compute with an explicit equation. So that's one way to prove this. So the final thing I should say is this is not a complete story for many reasons. First of all, this only works for diagonalizable group schemes. And push it further to linearly reductive group schemes, which are nice class, but in general you have to deal with more complicated ramification. And this kind of major problem. Another problem is you remember surface S, which are like this. And one would describe there is an easy action to some on X, which is this one. Let's take G invariance, and then it's completely unknown. Okay. So the problem would be to find some reasonable description between. Not much. Mysterious. And in the presence of wild ramifications, there are very interesting papers by Cobin when he looks at some examples. Get some results in this way. So I will stop here. Thank you.